last lecture we had, at the end of the last lecture, we were considering the solution of the Schrodinger equation for the 3-dimensional isotropic oscillator. We will, in this lecture, continue our discussion on that and make a few comments about the 2-dimensional oscillator, which is also a problem of great interest in quantum mechanics, particularly in the theory of magnetism, and then we will hopefully start on the Ket algebra formulation of quantum mechanics. So, we continue our discussions where we left off in the first lecture. In the previous lecture, we were considering a spherically symmetric potential, which is half mu omega square r square. It is a spherically symmetric potential. It is a spherically symmetric potential. In my previous lecture, I wrote this as half mu omega square x square plus y square plus z square and solve the Schrodinger equation in Cartesian coordinates and obtain the eigenvalues as E is equal to n 1 plus n 2 plus n 3 h cross omega. I am sorry. This we had obtained as E is equal to n 1 plus n 2 plus n 3 plus 3 by 2 h cross omega, where each of these integers n 1, n 2, n 3 can take values 0, 1, 2, 3, etc. Now, if I use this equation, then we can, as we had shown earlier, we can solve this equation 2 mu by h cross square E minus V of r psi, and we can use the method, we can use the spherical polar coordinates r theta phi to solve this equation. Since the potential energy function depends only on the r coordinate, we can write the solution as psi of r theta phi as r of r times y theta phi, where y theta phi are the eigen functions of the operator L square, as we had seen that y theta phi are the spherical harmonics, which are L square y theta phi was equal to L into L plus 1 h cross square y L m, sorry, this is also y L m theta phi. These are the spherical harmonics. So, if I substitute this in this equation, then you will get the radial part of the Schrodinger equation, and if I define a function r of r, u of r, such that r of r is equal to u of r by r, then u of r satisfies the following equations. This is the d 2 u by d r square plus 2 mu by h cross square E minus V of r minus L into L plus 1 h cross square by 2 mu r square u of r is equal to 0. This is the radial part of the Schrodinger equation. This is one of the forms of the radial part of the Schrodinger equation, and this simplification is always possible as long as the potential energy function is spherically symmetric. So, now we assume that V of r is half mu omega square r square, and then we write down, as we have done for the harmonic oscillator, that xi is equal to gamma r. So, this becomes du by dr becomes du by d xi into d xi by dr, which is gamma. If I differentiate this again, so you get d2u by d xi square multiplied by gamma square. So, I want to put this down in the denominator. So, plus, please see this, 2 mu e by h cross, or let me write this down here, then I will do it again. And this is half, my potential energy is half mu omega square r square. So, half into 2 cancel out. So, you get mu square omega square by h cross square r square. If I take 2 mu by h cross square out inside, so you get minus L into L plus 1 r square, u of xi equal to 0. So, I divide by gamma square. So, I get plus 2 mu e by h cross square gamma square. So, I will write this as capital lambda, where capital lambda is defined to be equal to 2 mu e by h cross square gamma square, and this becomes, let us see, r square is xi square by gamma square. So, this term becomes mu square omega square by h cross square, r square is xi square by gamma square, and there is one gamma square coming from here. So, this will become gamma to the power of 4. Now, I choose my gamma, so that this factor is 1. I have not yet, this is the same method that we had used in solving the harmonic oscillator problem. So, I choose gamma, so that this is equal to under root of mu omega by h cross. If I choose this value of gamma, then this coefficient becomes 1 and this becomes minus xi square. And the last term L into L plus 1 gamma square r square. So, that is xi square. So, minus L into L plus 1 gamma square r square. So, that is xi square, u of xi is equal to 0. So, gamma square, so from here gamma square is mu omega by h cross. So, this becomes 2 mu by e by h cross square mu omega by h cross. So, mu cancels out. So, you get 2 e by h cross omega. So, the Schrodinger equation simplifies to the radial part of the Schrodinger equation simplifies to d2u by d xi square plus lambda minus xi square minus L into L plus 1 by xi square u of xi is equal to 0, where xi is equal to gamma r, gamma is equal to under root of mu omega by h cross. Now, lambda is now the eigenvalue. So, lambda is equal to 2 e by h cross omega. You must remember that xi now goes from 0 to infinity, and of course, u of 0 will be 0, because at the origin you have r of r is equal to u of r by r. So, at r equal to 0, so u of 0 will be 0. These are the boundary conditions, and u of infinity is 0. Now, we use the same trick, same methodology as we had used in the hydrogen atom problem. As xi tends to 0, this term dominates, and you can the solution of this term is d2 u by d xi square minus L into L plus 1 by xi square u xi. This will be u of xi will be xi to the power of L plus 1, because if you differentiate this twice, it will be L plus 1 into L xi to the power of L minus 2 L minus 1. So, that is what it will be. So, as xi tends to 0, it behaves like this. As xi tends to infinity, it is this term which dominates. We had experienced this term in the harmonic oscillator problem. So, if you recollect that, so u of xi as xi tends to infinity behaves as e to the power of minus half xi square. So, this suggests that we try out a solution just as we did in our hydrogen atom problem, f of xi y of xi, where f of xi is equal to xi to the power of L plus 1 e to the power of minus half xi square. So, as you recall that we had u double prime is equal to f double prime y plus 2 f prime y prime plus f y double prime, and we can calculate f prime from here, f double prime from here, and we have to make one more. These are rigorously correct solutions, rigorously correct solutions. We make another transformation, that we define a new variable eta is equal to xi square, as we had done in the harmonic oscillator problem. If I substitute this for f of xi and then make a transformation eta is equal to xi square, then the y satisfies this equation, eta d2y by d eta square plus c minus eta dy, I leave that as an exercise to show this, minus a y eta is equal to 0, where c can be shown to be equal to L plus 3 by 2 and a is equal to L by 2 plus 3 by 4 minus lambda by 4. So, once again what I have done is that u of xi I have written as xi to the power of L plus 1 e to the power of minus half xi square into y of xi, and then obtained an equation for y of xi. And then we have, since there is a xi square term here, we substituted a variable we use the transformation eta is equal to xi square. Then this function y of eta satisfies this equation. As we all know, this is the familiar confluent hypergeometric equation. This is the confluent hypergeometric equation, and the solutions are the well behaved solutions are f 1 1 a c eta. And as you know, this is 1 plus a by c eta by factorial 1 plus a into a plus 1 and so on. If this series is not terminated, then for large values of eta it behaves as e to the power of plus eta. So, this infinite series once again is convergent, but if it is not terminated, if it is an infinite series, then for large values of eta it will behave as e to the power of eta, that is e to the power of xi square. So, e to the power of xi square times e to the power of minus half xi square becomes e to the power of plus half xi square, and therefore, the function will blow up. We cannot let that happen, and so therefore, a must be, therefore, this must be a polynomial, and since in the numerator you have a into a plus 1, then a into a plus 1 into a plus 2. So, a must be a integer, negative integer. So, we must have for the infinite series to become a polynomial, a must be equal to minus n r, where n r can be 0, 1, 2, 3, because if let us suppose a is equal to minus 2, then the first term will be a into a plus 1, the second term divided by something, then it will be a into a plus 1 into a plus 2. So, that will become 0. Not only that term, but all subsequent terms will become 0, and the series will become a polynomial. So, for the series to become a polynomial, a must be a negative integer, and so therefore, this must be minus n r. So, I obtain that a must be a negative integer. So, L by 2 plus 3 by 4 minus lambda by 4. So, if I multiply this by minus 1, so you get minus L by 2 minus 3 by 4 plus lambda by 4 is equal to n r. I take this to that side and I multiply by 4. So, I get lambda is equal to 4 n r plus 2 L 2 2 L plus 3. If you recollect that lambda we had put equal to, lambda was equal to 2 e by h cross omega. So, this is equal to 2 e by h cross omega, 2 e by h cross omega, and so therefore, I will have E is equal to, if I divide by 2, so 2 n r plus L plus 3 by 2 h cross omega. So, these are the rigorously correct energy eigenvalues, where n r and L both take the values 0, 1, 2, 3, L also take the value 0, 1, 2, 3, etc. So, as in the previous case where we had used Cartesian system of coordinates, we of course must get the same eigenvalues. So, you will have the ground state the ground state will be nr equal to 0 and L equal to 0, and so therefore, E will be equal to 3 by 2 h cross omega. Okay. And what will be the wave function? The wave function we had denoted that since L is equal to 0, so m will be equal to 0. So, my angular part will be y 0 0 theta phi. So, this will be just 1 over under root of 4 pi. So, this will be the angular part, and because my wave function is r of r times y theta phi, y L m theta phi. L is 0, then m will be also 0, and r of r will be u of r by r, and if I divide by, so this is the same as, so if I multiply by gamma, so u of xi by xi, and this will be with a normalization constant, this will be xi to the power of L e to the power of minus half xi square f 1 a comma c comma xi square. So, I write this down once again r of r will be xi to the power of L e to the power of minus half xi square f 1 a comma c comma xi square. If a is 0, with a normalization constant, a is 0. So, this is 1 and L is 0. So, this is just n into e to the power of minus half r square gamma square r square. This is my wave function. Let me do one more case and then we will end there. The second eigen function will be nr equal to 0, first excited state, and L is equal to 1. If L is equal to 1, the eigenvalues will be 5 by 2 h cross omega. So, your radial part of the wave function, the radial part of the wave function will be n xi to the power of L, that is r to the power of L. So, that is r gamma r to the power of 1, a is 0, and nr is 0. So, a is 0. So, this is 1. So, e to the power of minus half xi square but since y L is 1, so m can take values 1 0 minus 1. So, you will have this multiplied by y 1 1 y 1 0 and y 1 comma minus 1. So, this will be, as we had obtained earlier, threefold degenerate state. So, what we have tried to show you is that for the 3-dimensional oscillator problem, isotropic oscillator problem, one can solve the radial part of the Schrodinger equation in terms of the confluent hypergeometric function, and one, you give me the value of a and c, that is, you give me the values of nr and L, and I will be able to immediately give you a is equal to minus nr and c is equal to L by. So, a is equal to minus nr and c is equal to L plus 3 by 2. So, if you give me the values of a and c, I can immediately write down the polynomial and I can write down the corresponding wave function. So, it is really very straightforward. You give me any value of a, you give me any value of nr, any value of nr and any value of L, I can immediately write down the wave function within a normalization factor, and that can be easily calculated by using the normalization condition that 0 to infinity r of r mod square r square dr, from r equal to 0 to infinity, this must be equal to 1. So, finally, we consider the last problem in this series, and that is the two-dimensional harmonic oscillator. Now, if I have the two-dimensional, we conclude this lectures by considering the two-dimensional oscillator, and in which we will have the V as half of mu omega square x square plus y square. So, we have to solve the two-dimensional Schrodinger equation in terms of x and y or in terms of rho and phi, where rho phi are circular, are coordinates like this. Rho x is equal to rho cos phi and y is equal to rho sin phi. So, you have here x, y two-dimensional, and this is my rho and this is the angle phi. These are known as the circular coordinates. So, in this, if I take rho and phi as my coordinate systems, then I can write this down as half mu omega square rho square. So, the Schrodinger equation is in two dimension. Either I can write this down as delta 2 psi by delta x square plus delta 2 psi by delta y square plus 2 mu by h cross square e minus half mu omega square multiplied by x square plus y square psi of x y is equal to 0. And I leave it as an exercise. You again use the method of separation of variables. You write this down as psi x y as x of x and y of y. You will obtain Hermite Gauss functions, and the energy eigenvalues will be n 1 plus half plus n 2 plus half. So, n 1 plus n 2 plus 1 h cross omega. These will be the eigenvalues. N 1 is equal to 0, 1, 2, 3, n 2 will also be equal to 0, 1, 2, 3, etc. And the corresponding wave functions will be n's of n 1, h n 1 of xi multiplied by n's of n 2, h of n 2 eta e to the power of minus half xi square plus eta square. So, these are the Hermite Gauss functions. But since I can use also the cylindrical coordinates, and we will obtain 1 over rho delta by delta rho delta psi by delta rho plus 1 over rho square delta 2 psi by delta phi square plus 2 mu by h cross square e minus v of rho. V depends only on the rho coordinate, psi of rho phi. I can again use the method of separation of variables, and phi goes from 0 to 2 pi. So, the phi variable, so I can write this down as psi of rho comma phi is equal to the radial part times the phi part, and one will obtain a term like this. So, if I will obtain a term like this 1 over phi d 2 phi by d phi square, as we had obtained in the angular momentum case problem, we will set this equal to minus m square, and we will get phi of phi is equal to the normalized e root 2 pi e to the power of I m phi, where m is equal to 0, plus minus 1, plus minus 2, etc. So, you will have an equation which will involve only the rho term, and I leave it as an exercise for you. If you define any function which is such that r of rho is equal to u of rho by square root of rho, then u of rho will satisfy the following equation: d2u by d rho square plus lambda minus rho square minus m square minus 1 by 4 by rho square u of rho is equal to 0. So, the phi part will separate out, and you make a substitution like this. This is fairly straightforward, and one will obtain an equation like this. Once again, we look in the limiting form for rho tending to 0. So, this term will dominate, and you will have d2u by d rho square minus m square minus 1 by 4 by rho square u of rho, and the solution of this equation will be rho to the power of m plus 1. So, it will come out to be rho to the power of m plus half. So, if I differentiate it once, it will become m plus half times m minus half. So, that will be m square minus 1 by 4. So, therefore, the small rho behavior will be u rho, the same methodology will be rho to the power of m plus half, actually mod m, because here m square appears, times the large rho behavior will be again e to the power of minus half rho square and multiplied by y of rho. Then, because of this term, you introduce another variable which is eta is equal to rho square, and this we take g of rho, and we can write down just as we did for u double prime of rho will be equal to g times y double prime plus 2 g prime y prime plus g double prime y of rho, where the primes denote differentiation. And if you use this transformation, that eta is equal to rho square, then you will find that the solution is again can be written down in terms of the confluent hypergeometric equation, and for the confluent hypergeometric equation to get terminated, the solution will be f11 a comma c comma eta, and a will be equal to minus lambda by 4 plus m plus 1 by 2 is equal to minus n. For this to terminate, a must be equal to a negative integer. So, if you multiply by negative sign, so you get lambda by 4 minus m plus 1 by 2 is equal to n. So, lambda will be equal to, this is equal to 2 e by h cross omega. So, this will be 4 n plus 2 modulus m plus 1. So, E will be, if I divide by 2, so this will be 2n plus m plus 1 h cross omega. So, if n is 0, m is 0, then you have the ground state energy eigenvalue as we had obtained earlier. But these solutions are of extreme importance in considering the effect of the magnetic field, and so what we have done is that we have, to summarize, that we have considered a 2-dimensional oscillator. We can solve this by using the method of separation of variables, and then or we can use the circular coordinates where x is equal to rho cos phi and y is equal to rho sin phi. If we do that, the corresponding del square operator in 2 dimensions becomes this. We can use the method of separation of variables. So, this becomes d2 phi by, so this term will separate out. If you multiply this equation by rho square and then divide this equation by r times phi, you will have a term which depends only on phi, and the remaining terms will depend on rho. So, the phi term we set equal to this constant, and the phi solution will become, as we had obtained in the angular momentum case, 1 over root 2 pi e to the power of I m phi. So, with that we make a transformation something like this. We look at the small rho behavior. Small rho behavior will be rho to the power of m plus half. Large rho behavior will be dominated by this term. So, this will be e to the power of minus half rho square, and therefore, we will try out a solution like this, and then we will substitute eta is equal to rho square. We will, I leave it as an exercise, it is a very simple exercise, and you will get the confluent hypergeometric equation. And that confluent hypergeometric equation, the function must be terminated, otherwise this will behave, if this series is not terminated at large values of eta, it will behave as e to the power of eta. So, therefore, this will behave as e to the power of rho square, because eta is equal to rho square. Rho square, if you multiply this here, it will become e to the power of half rho square. So, the wave function will diverge at rho equal to infinity. We cannot let that happen, and therefore, a must be a negative integer, and so therefore, a, which is given by minus lambda by 4 plus m plus 1 by 2 must be a negative integer. And so, therefore, these are the eigenvalues of the problem, and the eigen functions can be written down in terms of the confluent hypergeometric function a c rho square times e to the power of minus half rho square times rho to the power of m plus half. Let me write it down clearly. So, the wave functions. So, the final energy eigenvalues will be E is equal to 2 n plus m plus 1 h cross omega, where n is equal to 0, 1, 2, 3, m is equal to mod m 0, 1, 2, 3, etc. And the wave functions will be psi of r phi or rho phi will be rho to the power of m plus half. So, if I divide by square root of r, then the half goes away, e to the power of minus half rho square f 1 1 a comma c comma rho square, where a is equal to minus of n. and so and C is equal to mod m plus 1. So, these are the phi dependence. Of course, there is a normalization constant here, and the phi dependence will be 1 over root 2 pi e to the power of I m phi. This is the phi dependence, this is the rho dependence. These are the rigorously correct solutions for the harmonic oscillator, for the two dimensional oscillator problem. And as I told you that the ground state corresponds to n equal to 0 and m equal to 0. So, this is equal to 1. So, this completes the solutions of the one dimensional Schrodinger equation and sometimes the two dimensional Schrodinger equation, and of course, the three dimensional Schrodinger equation. We have solved the hydrogen atom problem, the three dimensional oscillator problem, the diatomic molecule problem, the linear harmonic oscillator problem, and also we have considered tunneling through a barrier and things like that. So, this is one aspect of a very important aspect of quantum mechanics that we have considered. We also considered the free particle problem and propagation of wave packets. In the following few lectures, we will consider yet another formulation of quantum mechanics. It is by Dirac, and it is for understanding this, one must be very familiar with the rules of matrix algebra. So, we will carry along. So, we will try to tell you all the steps. For example, let us consider the harmonic oscillator problem, V of x, linear harmonic oscillator problem, and we have the potential energy distribution is like this. So, we have a parabolic index potential, and we had obtained that these are the discrete eigen. So, this corresponds to n equal to 0, n equal to 1, and this is equal to n is equal to 2, and similarly n is equal to 3. This was denoted by the wave function, this psi 0 of x, psi 1 of x, psi 2 of x, and so on. Now, we consider this linear harmonic oscillator. These are the different states of the oscillator. Now, what Dirac said was, each state of a dynamical system is represented by a ket vector, and we denote this by a ket like this. So, this vector, this state I denote by ket 0, this state by ket 1. I have hydrogen atom states also. We had solved the hydrogen atom problem. Each has a specific quantum number, set of quantum numbers. Now, each state of the hydrogen atom I represent by a ket vector. So, let us suppose this state I represent by ket vector A, and another state by a ket vector B. So, each state of a dynamical system is represented by a ket vector such that any linear combination of these two vectors is also another vector in the same space. I will detail this little later. Corresponding to each ket vector, there is a bra vector A such that we can form a scalar product which is bra A B, and this quantity is a complex number. So, that we say that each state of a dynamical system I represent by a ket vector. There can be many ket vectors associated with a state. One can take a linear combination of these two ket vectors. Corresponding to each state ket vector, there is a bra vector A such that we can form a scalar product A B, which is a complex number, and is such that the complex conjugate of this number is denoted by B A. It may appear a little abstract, but I will give you an example in a moment. Now, let us suppose I put B is equal to A. So, then this tells me this is an axiom. Then I have bra A ket A, which is a number. So, this is A times A. So, which tells us that the scalar product of a ket vector with its own bra is a real number. I further say that not only this is a real number, but this is always positive definite, that is, this is greater than or equal to 0, unless A is a null ket. Now, what is a null ket? A ket vector A is a null ket when, if pre multiplied by bra B, if this is 0 for any bra B, then ket A is said to be a null ket. Sorry. Similarly, bra B is a null bra if and only if bra B ket A is 0 for any ket A. Let me try to make you understand the concepts that I have developed using matrices. Now, I consider a two-dimensional space. So, I have a column vector representing a vector A, a ket vector A. I represent this by, say, A B. Another vector B, I represent this by C D. I forgot to mention here that if A B is 0, then A vector A ket A and ket B are said to be orthogonal to each other. The scalar product is said to be 0. If bra A ket A is 1, then we say that the ket vector is normalized. So, let me go back to this, to a two-dimensional space where a ket vector is represented by A B, two numbers, and bra B also, Ket B also belongs to the same space, two dimensional space. So, you can write down A plus B will be again in this another vector in the two dimensional space. So, if this is 1, 2, 3, 4, so this will be 4 plus 4 here and 5 here. Now, corresponding to this bra A, corresponding to this, the bra A will be the complex conjugate of this and this. This is known as the dual vector space. Corresponding to a column vector, there is always a row vector. And if I multiply these two, bra A ket A, it is a number. So, you will have A star B star A B. So, this will be mod A square plus mod B square. So, this is always greater than 0. It can be 0 if and only if A is 0 and B is 0. So, then that is a null ket, because if you have a null ket, you can multiply this, pre-multiply by any bra, and this will be 0. Now, here bra B is equal to C star D star, and the same analysis I can do. Now, if I have bra A ket A, if this is 1, that is, if mod A square plus mod B square is equal to 1, we say that the ket is normalized. So, let me give you an example. So, let me take a ket A which is given by again a two dimensional space, 1 by root 2, 1 by 1, 1 1. So, these are both real numbers. So, bra A is equal to 1 over root 2 1 1. So, bra A ket A will be 1 over 2 1 1 1 1. So, that is 2 and that is 1. So, we say this is a normalized ket. Now, we take another ket B and we write down 1 over root 2 1 minus 1. So, as you can see that this ket is also normalized. However, if I now do B A, then 1 over root 2 multiplied by 1 over root 2 is 1 over 2, and bra B is 1 minus 1, and ket A is 1 1. So, this is 0. So, we say that ket A and ket B are orthogonal to each other. Let me give you another example. So, let me write down, there is another vector in the same space C, which is equal to 1 over root 2 1 minus I, and I leave this as an exercise where I is equal to square root of minus 1, that this is a normalized ket, and if I take another ket D is equal to 1 over root 2 1 plus I, then this and this are orthogonal to each other. But if I take a ket A which is 1 over root 2 1 1, then that is not orthogonal to either of these vectors. So, we will continue our discussion on bras and kets in our next lecture, but before that I will request all of you to brush up your matrix algebra, because the operator algebra that we will develop, it will be very easy to understand that if we have a knowledge of the algebra involved with matrices. Thank you.